Hi everyone. Good afternoon, everyone. My name is Gabriel. I'm actually a first semester post-graduation PhD student from the post-graduation program in physics here in Natal. And today I'm going to talk very briefly about one of the branches I'm working on my PhD research with Professor Gandhi. It's basically topological data analysis applied to complex systems. So just a little brief motivation. We have this plot here, this very beautiful plot for this very beautiful paper from this Journal of Cloud Computing, where you can see this exponential increase according to the Moore's law in the data volume in zettabytes across the years. So basically we are in the big data regime. So we need techniques to handle this big data like smart data, natural language processing, generative models, and so on. And topological data analysis will play an important role there. So what is the core idea of topological data analysis, aka TDA? Well, the idea is very simple. It's basically data has shape and shape has meaning, so data shapes matters. That's basically this. And if I can simplify this in a very simple way, basically is you have your data and you can translate your data in some kind of shape. In other words, the idea is to assign topological invariants to your data or boil down your data to essential elements. So if I need to summarize the TDA pipeline in a simple way, I will do this. So essentially, take your data, translate your data in some kind of shape, and extract some kind of topological features from this shape, like the number of nodes, the number of edge, and homology groups, or the bit numbers. And you can do all your analysis, your statistical analysis, your machine learning, deep learning, artificial intelligence analysis with this. So feel free to do what you want. Another motivation, this is some works. We have some applications in medicine for mapping cancer subtypes for using TDA. We have an application in sports for role classification in NBA, and also in politics for political evolution in the USA. So I think it's very interesting. This looks very cosmetics, but it's basically a very pure mathematics degree. That's why I love pure mathematics, because I also a mathematician. But I will not do this. I will you'll be a little more non-aggressive today. So first of all, I want to talk a little about this algorithm. This is called the mapper algorithm. The idea is quite simple. Basically, take your data and project and use whatever dimensionality reduction method, PCA, TSNA, you map, you choose to project your data in a lower dimensional space and apply a filter function to make discovers. Essentially, some kind of sets that have overlaps between points. So when you do discover, you map back, use an inverse filter function. This is what we call lens in your data, and apply a clustering algorithm. Choose algorithm you want, k-means, Monte Carlo methods, you choose, and you create this cluster per image. And now translate this in some kind of graph with each node, it's a cluster. And if this cluster shares at least one member, or in other words, one data point, you put a link. So this is, and now you can do all your graph theory analysis. So this is the map algorithm, this most simple algorithm. But today I'm gonna go in another way, and I know that some people doesn't like this very much, but I'm going to talk a little about simplex. Well, it's very simple. It's the generalization of the concept of triangles. So we have 0 degrees simplex as a point, a 1 degree simplex is a line, a segment line, sorry. 2 degrees simplex is a triangle, 3 degrees simplex is a tetrahedron, and so on, and you can make your infinite degree simplex. Just a terminology, a collection of simplex is what we call a simplicial complex. Just a terminology. And why this? First of all, we want to talk about holes. It's a way to characterize the shapes in topology, in particular in algebraic topology. So we are basically talk about connected components, holes and cavities, some kind of holes in 0, 1, 2, and n dimensional. And we can assign to each one of these topological structures some kind of groups, 80, 81, and 82. Essentially is what we call the homology groups. In a non-mathematician way, is a way to characterize holes. Okay, so essentially when I say homology, you can interpret like holes. And one of the most interesting, well, at least for me, fields we have, methods we have in TDA is what we call the persistent homology, where the idea is, well, quite simple. You have your data points and you are create some circles with some radius epsilon on this point. And when you have overlap between these circles, the radius of the circles will be increased. And when you have your overlap, you create a link. And also, or in other words, you are creating a connect component. And you can visualize this in what we call a persistent diagram. So this is an animation I have made. And this is the radius when you have a depth of a certain topological structure. And this is the radius when you have the birth of a certain topological structure. Just another example, this is the persistent diagram of points sample along the surface of a sphere. And this is a points sample along the surface of a torus. And a very interesting thing is, this is a theorem from TDA. We can show that points that are sampled across this, that falls in across this epsilon equal x line are basically noise. So it's a method that's robust to noise. Well, this is an example I developed on the last few days. Just to bring here is basically gravitational TDA to gravitational wave detection, basically to time series analysis. So we have a time series of frequency here, and this is my raw data, and I can separate this in what we call a pure noise time series and a not pure noise time series. In my not pure noise time series, I can separate in the signal and a background. Okay, what are we gonna do? So I have two time series, pure noise and not pure noise, and I can use in TDA techniques like Takes embedding, sliding window time delay, persistent homology, and so on, but to construct a topological representation of this time series. Well, pure noise time series very obviously is basically a ball of random points, but the interesting thing is here. We can see this very beautiful structure. But it's not just cosmetics, because when you look a little more closely, we can see this is spirals here. The color here represents how much closer a point is in the original time series. So we can see that these spirals here represents just this decaying periodic signal. So decaying periodic signals emerge as spirals in my topological representation. But there's something that is very, very more interesting. Look at this point here, but it's not a point, it's a cluster. This cluster here is basically this region here. And why this region is important? Because this is the region when I have the merging of these two non-spinning black holes. So this is the region when I have gravitational wave generation. So I can detect in a more simple way gravitational wave. Actually, this is basically illustrates in a more feasible way the dynamics of my system. And this is very interesting because it's doing just data analysis, observational astronomy data analysis on this time series is very complicated, and I can say that because I'm from astronomy. I'm from astrophysics. Great, and you have an entire new world of applications. Well, another application I developed is basically you can do this in dynamical systems. This is the Lorentz attractor, but you can do all your dynamical system approach. Another interesting approach that I think is using this on hydrodynamics, magnetohydrodynamics, and so on. Another very interesting application, 3D shape classification. This is very interesting, like tomography, for example. But the most interesting application I have found, I think, is this cosmic web. Basically, these black points here is basically the data for the observable universe from the Slow Sky Survey. It's a ground-based telescope that maps the observable universe. And these filaments here are H1 homology groups, and these are H2 homology groups. So this is very interesting because I can map my observable universe and I can relate this topological structures to some astrophysical process like globular clusters, open globular clusters, compact systems, coronal jets, and so on. And this is very interesting because I can use 3D shape classification to, for example, classify morphology of galaxies, for example. In galaxy morphology, it's a very complicated to model. So, thank you for your attention. I will happy to answer all your questions under the constraints of the limitation of my knowledge. So, thank you.
Okay, thank you very much. He said 10 minutes. It was 10 minutes to the second. I'm impressed. So we have plenty.
It was really 10 minutes?
Yeah, precise, to the second. So 9:59, bam. And you said thank you. So we have plenty of time for questions at this point. One.
Oh, no.
Hi, it's indeed very interesting, very, very curious. My question is that it's not exactly similar, but have you ever heard of or worked with visibility graphs?
I'm not very sure.
No, it's a method for you can analyze like a time series, you transform it into a complex network, and then you can analyze properties from this time series by analyzing like clustering coefficients, near degree neighbors for the networks.
Okay.
It's not exactly what you do, and the visibility graph is only applied to time
Well,
series. Sorry.
I work a little with graphs, but I'm not a specialist on this field. But my interest in using TDA is because I'm interested in topological deep learning, and so I use this to construct, simplicial neural networks, and this is my interest in. I spoiler of my PhD. Basically, please don't take my idea. The idea is. I want to apply these methods across scales. So let's use these techniques on quantum scale, on mesoscopic scale, and astronomical scale, and let's see if we can find some, classes of universality. Look at the topological structure. Well, this is what I want to do on my PhD. I mean, I am a newbie. I'm a first semester PhD student, so let's see.
It's just because it reminded me. It's not the same, but it reminded me of the philosophy of visibility graphs. I have a friend that works with it, so maybe you might be helpful. I don't know.
You can do.
Yeah.
Yeah, you can make all your graph stuff here, basically using the map algorithm, for example.
Afterwards, I'll talk to you afterwards.
Great.
Thanks.
Very good. There's another question coming up.
So very nice presentation. Really, I really liked it, and indeed, as Hugo said, very interesting. I just wanted you to elaborate a little bit on the step that you take to from the projection of the data to the cover. How do you really build that, or is there multiple ways to do that?
Well, there is a method. It's some kind of pipeline. Basically, essentially, this is what we call a lens in TDA, but essentially you can optimize this cover to construct this. You could translate this is like a semi-definite linear programming, and your optimization among of that. This is essentially this is a some kind of a linear or non-linear programming. You can optimize this. I will not go. I didn't bring this because there is a lot of mathematical stuff, and I don't want to scare anyone.
Yeah, that's fair. Okay.
Any more questions? We had time. Yes, we finished kind of early, so. No. So you said that's like linear programming.
Yeah, you can
finding a solution, linear programming, particularly if you are trying to discretize the space and you end up with integer linear programming, is NP hard. So how slow are these algorithms when you are trying to analyze, for instance, the sky survey that is like a ton of data?
Yeah, well, this is one of the methods. I mean, the paper of the Sloan Digital Sky Survey doesn't use in this method. They use in the persistent homology.
You are going to use the method because you're the PhD student, right? So
no. We have a lot of methods. This is one of the methods. And we have, I didn't bring here, but there is a way to apply topological data analysis to time series. And there is a lot of stuff like takens embedding, basically as a takens theorem. We will take your data analysis and map in a high dimensional space, like that's the one name, and you can discretize this using what we call a sliding window time delay. When you need two parameters, the time delay, and you can optimize the time delay, find the first minimum of the mutual information of your time series, and you have the dimension of your graph. Obviously, this is just a 3D representation. You apply a PCA and you can visualize this, but this is a high dimensional, and the dimension you can find the first minimum of inequality of the polytope and use a method called the false nearest neighbor. So it's a lot of things in 10 minutes is very, yeah, it's very short for apply of this. My idea was to show that, oh, this is a very interesting method and this works, especially for astrophysics because I'm from astrophysics, so I have this high level bias on my, yeah. Yeah.
Okay, pretty cool, pretty cool. All right, we can, I guess, thank the speaker once more, and we have Esteban. There you are.